Hi everyone, welcome back to a new video. So in this series or in this complete tutorial, you're going to learn about the most important concept is big O notation. So in this tutorial, okay, we are going to spend a lot of time on big O. It's a huge topic when it comes to data structures and algorithm. So what is big O? BigO is a way of comparing two sets of code, and let's say code 1 and code 2 accomplish exactly the same thing. How do you compare one against the other? Code 1 might be more readable, that might be better. Code 2 might be more concise, the code might take up fewer lines, and if that's what you're measuring, then you would say that code 2 is better. BigO is a way of comparing code 1 and code 2 mathematically about how efficient they run. In a coding interview, you will absolutely be asked questions about BigO. So let's look at what BigO is. Let's say we have a stopwatch and we run code 1 and we start the stopwatch and it runs for 15 seconds and we reset the stopwatch, then we're gonna run code 2. So the code 2 runs a lot longer than 15 seconds. It may run for a full minute. Based on this, you would say that code 1 is better than code 2. You can measure it. This is called time complexity. The thing about time complexity that is interesting is that it's not measured in time. Because if you took the same code and run it on a computer that runs twice as fast, it would complete twice as fast. It doesn't make the code any better, it just means the computer is better. So it is measured in the number of operations that is that it takes to complete something. And we look at example of that as we go along in this entire tutorials or the series. In addition to time complexity, we measure space complexity. So let's say that code 1, while it runs very fast comparatively, let's say it takes up a lot of memory when it runs, and maybe code 2, even though that takes much longer to finish, maybe it takes up less memory. In preserving memory space is your most important priority, then you don't mind having extra time complexity. Maybe code 2 is better. So when you get into an interview, there's a good chance that you'll be asked question about time complexity. And then they'll say, hey, well, what if space complexity is our main priority? How do you approach it then? You have to understand both concepts and be able to address that in the job interview. You have to understand both concepts to be able to address that in the job interview, right? But for the most part of this class, will be dealing with time complexity, and that is our quick intro to Big O. So, welcome to episode 2. So when dealing with time complexity and space complexity, you will see these three Greek letters. They are omega, theta, and umicron. Is better known as O as in big O. And to show how we use this, I am going to bring up an array. So say we are going to use a for loop to loop through this array. So when we are looking at how many times that we have to run the for loop, our best case would be if we are looking for the number 1, and our worst case would be if we are looking for the number 7, and our average case would be if we are looking for the number 4. So this best case with the number 1, for that we use omega, and for the average case we use the Greek letter theta, and for our worst case we use the Greek letter omicron or big O. So One of the things people will say when you talk about your big O being a particular time complexity is they'll say things like, yeah, but what is your average big O or your best case big O? Well, technically, there is no average case or best case. Big O average case would be theta and best case would be omega. But you will hear people sit in the way, but technically big O is always a worst case. Now let's look at our first big O notation. It is O of n and I'll start with O of n because it is the most efficient or the least efficient. I'll start with this because I think it's the easiest one to get our head around. So to explain this, I am going to use a simple method. We are going to call it print items method. Okay, we'll pass it an integer n, and then we have a for loop that is going to run n times, and then we will print out it from the loop from the for loop. So now let's go take a look at this in editor. So here is that method there, and then we are going to down here to run the method with the number 10, and I'll run this, and you can see over here that it printed 0 to 9. So it printed out 10 items. So let's get flip back. So this code here is a within is O of n, and the reason that is O of n is we had a number of n. In this case it was 10, and then we did 10 operation and our for loop. Now let's look at O of n on a graph. Okay, so this is the graph. On this axis this is in, and this is the number of operations. O of n is always going to be a straight line. It is what is called proportional. So as we move to big O section, we will add different big O to this graph. So we can compare one to another. But for now, that is O of n. Welcome to episode 4. So in big O, we have few ways that we can simplify things. And the first of those that we are going to look at is drop constants. So let's bring up the method that we had in the last topic that looked like this with a single for loop. So, and with this we'll add a second for loop, and both for loops are going to run n times. So to run this, let's flip over to the editor. So there is our new print items method there, and once we again go down here, we are going to run this with number 10. I'll run this now, and you can see here that is printed out 0 through 9 here, and then it printed out 0 through 9 here again. Okay, so let's flip back. So in this case we had n plus n operations. We passed this 10 items and it ran 20 times, which is 2n. So might think that this would be O of 2n, but we simplify this by dropping the constants, and it just become O of n. And it doesn't matter if the constant is 2 or 10 or 1,000. We're going to remove it and just leave this O of n. So first rule of simplification is drop constants. Now let's look at O of n squared. So I'm going to bring up our code from our last example here. This way a for loop followed by another for loop to make this code O of n square. All we have to do is make it where one for loop is inside another for loop. So like this. Now let's flip over to the editor and take a look at this. So this is our method there with one loop of inside another for loop. And I want to point out this particular line of code. There it's important to have these quotes because it turns the whole thing into a string. If you don't, it's going to take I and j and add them together as integers, and you are not going to get the output that you expect. I'm going to run this, and then over here I'm going to scroll up to the top. Here we get 0 and 0, and it goes all the way back to the down. Here we get 9 and 9. So now let's flip back. So these for loops ran n times, or for loop ran n times, okay, or n squared. So we passed this a 10 and we had 100 lines that were output, and that is O of n square. So now let's take a look at this one is on the graph. So you can see compared to O of n that O of n square grows much faster, and that means from a time complexity perspective it is less efficient. So if you have a situation where your code is O of n squared and there's a way of rewriting the code, it make it O of n, that is huge gain in efficiency. So that is O of n squared. Welcome to episode 6. So now we are going to look at another way that we can simplify big O. That's called drop non-dominance. So to illustrate this, I'm going to start with our nested for loop that we saw this previously, but I'm going to add an additional for loop after this. So we have our nested for loops above and a separate standalone for loop down here. So let's flip over and take a look at this in editor. So there is our method there, and we'll call this down here with the number 10, and I'll run this. Okay, so I'm going to scroll to the top here, and you can see it starts with 0 0 and then goes down here where it goes to 9 9, and then we have 0 to 9. So now let's flip back. So this nested for loop ran O of n squared times, that was 0 to 9, and this for loop ran O of n times, so the total number of operation was n squared n squared plus n. So that would be O of n squared plus n, but as n gets larger the n square grows much faster than the n. So even if we only took this to 100, the n squared operation would be 10,000 operation, and that's standalone. So n would be 100 operation. So the n squared is dominant frame and the n is non-dominant frame, and as n becomes larger and larger, you can see that standalone ends start becoming irrelevant. So we drop the n, and this this rule of simplification gonna be prop non-dominant. Welcome to episode 7. So we are going to take a look at O of 1. So I'm going to bring up a method that we are going to call add items. So we'll pass it an integer n, and we are going to do is return n plus n. So it doesn't matter if n is 10 or n is billion, there's only going to be one operation, which is addition. That is O of 1. With what we have seen before, as it grows, the number of operation grows in this situation. As n grows, the number of operation will stay the same. So let's change this from being n plus n to being n plus n plus n. So we have two operations. So we could call this O of 2. As you as you may have guessed, we are going to simplify this and call it O of 1. O of 1 is also called constant. It doesn't matter necessarily mean that there's only going to be one operation. It means that as n grows, the number of operations stays constant. So let's take a look at this on a graph. For 1 is just going to be a flat line across the bottom. This is most efficient big O. If you can do something in O of 1 time, it's always going to be much more efficient than anything else. And that O of 1. Welcome to episode 8. Now, let's take a look at big O of n. And to explain this, I'm going to bring up a sorted array, and to do what we are going to do here, the data doesn't has to be sorted. So let's say we want to find a particular value in this array. We say we are going to look for the number 1. What is the quickest way to narrow this down to get to that 1? Well, the quickest way would be to cut the array in the half and see if 1 is in the first half or the second half. So it is not in the second half, so we do not have to look at any of those numbers, so we can remove those. And that may not seem like a big deal when you have an array with only 8 items in it. But if you had an array with a million items in it, that's half a million items that you don't have to look at. So that is pretty big deal. So then we can take the array and do this again, and we know it's not on the second up, so we remove those, and we'll do the again, and then we'll find the number that we are looking for. So let's bring back all the other items in the array. So look at how many steps this took to find the number 1. First it was 1 and 2 and 3 steps. And remember, we had 8 items in this array, and it just so happens that to the third power is 8. So now I'm going to take this equation and turn it into a logarithm, and we are not going to get really deep into this math. This will be pretty simple, but when we convert this to a logarithm, it looks like this: log sub 2 of 8 equals 3. And I'm going to put this back, and let's look at this again. Log sub 2 of 8 equals 3. Let's look at this again. Log sub 2 of 8 equals 3. So what this basically saying is 2 to the what power equals 8 to the what power equals 8. Well, 2 to the third power equals 8. To put it another way, if you look the number 8 and or repeatedly divided it by 2, how many times it would get down one items it would take get down to one item. So that is 3 times. But the real power of this is when we are dealing with very large numbers. Let's say we take log sub 2 of this number. This is over a billion. How many times would you need to cut this number in half, get down to one item? And it is 31 times. So could have an array with over a billion items in it and find any number in that array in 31 steps. And that is the power of O of log n. So let's take this and look at it on a graph. So you can see that it is very flat, very efficient. It is also efficient as O of 1 of the course, but it is the it is the next best thing. So everything we are going to look at this course is going to be one of these four, except for I'm going to show one another one here, and this is O of n times log n, that is used with some sorting algorithms. So we're going to see this with quick sort and merge sort, but another other than that, everything else will be of these four. So that is O of log n. So our next rule for big O is different terms for inputs. So what I'm going to do is walk through some code that we have seen before, and then we're going to make some changes to it. So the code that we saw before is when we have a for loop and then we follow it with another for loop, and then we say each of the for loops runs in n times, and we would say that O of 2n, except we are going to drop constants and it becomes O of n. So the change we are going to make to this is, instead of passing this one argument, we are going to pass it two arguments, and then we are going to say the first for loop is going to run 8 times and the second for loop is going to run b times. And this is very popular gotcha interview question, and the reason is because you see a for loop and you say okay, that's O of n. Here is another for loop that is also O of, and then we'll add them together and that becomes O of 2n, and we drop the constant and this is O of n. But that is not correct. If you think about this from an algebraic standpoint, you cannot say that A is equal to n and B is also equal to n. So would have to say that this is O of n and this is O of A and O of B. And when you add them together, this becomes O of A plus B, and this is as far as you can simplify this. And the reason for this is, if A was 1 and B was billion, this would be very different for loops. And you have to understand how each one works to understand the same. They understand the time complexity for the entire method. Likewise, if we took these for loops and instead of having them one after the other, we had them one side of the other, this would becomes O of A times B. So we can't just say that each of the terms is in, we have to use different terms of inputs. Hello everyone, welcome to episode 10. So in this video, we're going to learn big O of array list. So I'm gonna use array list instead of arrays here.
All this concept, I need a data structure that's going to be dynamic and allow us to add new items and not just be fixed length, and lot of concepts that I'm going to show here will apply to arrays as well. Also, instead of showing our array list like this, I'm going to represent it like this so I can show the indexes. Now we'll just walk through some of the methods for array list and what the big O of those methods are. So now we'll start out with my array list of my array list. So say dot add the number 17, that's going to do this. And when we add something to this end of the array list, so it's pretty simple process because we don't have need to be changed. Likewise, when we remove this item with a dot, remove at the index of 4, and we remove that, there is nothing that needs to be re-indexed in the array list. So it is one operation to add something, it is one operation to remove something. So this is O of 1. This is different. If we do something on the other end of the array list, so we say my list dot remove the item at the index of 0. This one right here, when we remove this problem that we have, is no longer at the correct index. So we need to change the index of 1 here to be an index of 0, and then we need to do this all the way down, touch every item in the array list. So if we add an item at the index of 0, we bring that 11 back, we need to change this index, and then we have to do all this way down to make the room for that 11 to be index of 0. So in this case, n is the number of items in the array list, and because we had to touch each item, that means this is O of n. And because we have to touch each item, that means O of n, so it's O of 1 on this end when we are adding something or removing something, but it's O of n to do those things in the end. So when we remove that item, we have to be re-index every here. If we bring it back, we have to do all the re-indexing again to bring it back. So it's one of and it's O of n on the other end. So if we say my list dot add at index 1 the number 99, that's going to be indexed here, we are going to drop the number 99 here. We do here re-index that item, that make that at 2, and this is a 3 and that 4, and we have to touch all the items that come after where the insert happened. So that's O of n. So you might say that there should be O of half n, because on average the insert is going to be somewhere in the middle and you will have to touch half of the items. However, there is a problem with the logic. First, O of measure worst case, not average case. But even if O of half of n was our worst case and half is a constant, we drop constant. Like otherwise, when we go to remove that item, we are going to have the re-indexing every time, and so now it look something by value. Let's say we are looking for the value of 7. We start the beginning of the array list or the array, and we say this is the value of 7, this is 11. We are going to move until we get the value of 7. So we are looking the item by value is O of n, but it's different. We are looking by index. If you're looking for the index of 3, we don't have to iterate all the ways through this. We can directly to this index, and that is O of 1, and that is
Big O of array list.